in and people still hate proc power, and like, you know, we don't want either GPUs or non-GPUs. Something happens and they start attacking the network and we want to just move over to ETH2 quickly, then like this is what an emergency transition would look like, right? Basically, what you would do is we would need to have ETH2 kind of start having ETH1 blocks starting from some point in time, right? So there would need to be some point in time, and after that point in time, you would just start having kind of an ETH1 data field that just is part of ETH2 blocks. This could be kind of formally designated as a shard, but if this happens before phase 1, then there would not be shards, but that's fine. We could just add this data field to the beacon chain. Now, as part of this data this field, we would of course also have to add state roots. And from a state transition point of view, like the state roots still work in exactly the same way, and it would actually be a validity condition of this chain that the ETH1 components are still fully valid. Now, if we do this transition kind of really ASAP, right, so like within this year, then ETH1 is not going to be stateless. And so basically every ETH2 node would need to have the full ETH1 state. And this would be not very nice because the ETH1 state is bulky and we're looking to try to make ETH2 be kind of much more accessible and much lighter than ETH1 is. And so at least initially that would kind of temporarily stop that objective. But over time, we could, of course, go and make the ETH1 inside of ETH2 stateless again. So basically, you would just, before you would have your blocks inside of here, and then after this chain would just kind of not be used anymore, and then you would have blocks inside of here. Now, the challenge, of course, is like, how do we handle this particular moment in time, right? So basically, the challenge here is that we need to decide on a kind of an ETH2 side cutoff, and we need to decide on some ETH1 side cutoff. And you want the ETH1 side cutoff to happen before the ETH2 side cutoff, so that basically by the time this happens, everyone on this side would be able to have consensus on basically which initial state root to kind of import over here as the beginning state, right? So at this point in time, like basically every ETH2 node would have to also be an ETH1 full node, and it would have to have the ETH1 full state so that it can start processing blocks. So what ways do we have of doing this, right? So first of all, the ETH2 chain already has ETH1 data voting, right? So we already have a mechanism by which the ETH2 chain is kind of aware of particular ETH1 blocks. And so in order to make a transition, one of the things that we can do is we can just piggyback off of this mechanism, right? So we can say, for example, something like, if the ETH2 chain discovers an ETH1 block whose block number is greater than or equal to n, or then and that gets approved by the ETH2 voting mechanism, then some procedure kicks in, and then possibly after some period of time, you declare what the ETH2 cutoff is, right? So basically, the ETH2 chain watches ETH1, and eventually there's going to be an ETH2 block that detects that the ETH1 chain has reached some cutoff point, which is defined by rules that exist inside of ETH1. So, for example, it's ETH1 voting on a block whose block number is greater than the cutoff, and then at that point in time, there might be some further delay, and if you have an ETH1 block, you would have its state root, and so you would have consensus on what state to start from. Within that period of time, everyone would have to kind of update to that state, and you would continue from there. So I'll stop for a bit. Any questions on this transition step? Okay, I want at least one question. Yes? How do you get the last? So basically by using the ETH1 voting mechanism. mechanism, right? So ETH2 already has a mechanism by which the ETH2 chain is aware of some ETH1 block, and that block keeps on increasing over time. And the idea would be that we would expand the ETH1 voting mechanic so that it's also kind of directly aware of not just the block hash, but also the state root and the block number. And whenever the block number is greater than the cutoff, then like this mechanism would kick in.
What I mean is, say, like the cutoff is not 12 million.
Right.
So miners have like some incentives there.
Oh, yes, that's okay. Good question. Miner incentives. So basically, if we kind of socially agree that no block after block 12 million kind of counts, right? So then the other thing we'd have to do for this to be safe is we'd have to like do a soft fork or some kind of fork that just bans transactions after block 12 million or whatever, because the ETH1 voting might end up like choosing a block after 12 million. Then miners need some incentive to continue mining. The simple and dumb suggestion that I have, if we want to be lazy and do little work, is that I think the Ethereum Foundation should just donate 2 Ether to every miner that generates a block that's part of the longest chain for some time after 12 million. And that allows us to just maintain an incentive that's exactly the same as the incentive that exists today. And we can keep that running for like some number of hours, whatever period of time is necessary to do a smooth transition. If we do not want to do this, then we could do something slightly more complicated and do it in protocol, right? So either way works. Yes?
Couldn't a specific hash be like hard-coded inside the Ethereum client code?
So the challenge there is that massively increases the amount of time between the within the cutoff, basically because you would have to coordinate a hard fork on the ETH2 side after the ETH1 chain already finished, right? So because we're expecting there to be dApps and we're expecting there to be optimistic rollups and like, I heard Arbitrum is going really crazy with a challenge period of 4 hours. I haven't personally confirmed this, but there may be applications doing things like this. So like, the closer we can get to having a very short transition time between here and here, the better. Yes?
Is the shortest like the sort of 1,000 blocks that the beacon chain watches? Or can we do shorter than that?
Can we do shorter than the 1,000 blocks that the beacon chain watches? I don't know. I'm not sure if it's necessarily a good idea to do shorter than 1,000 blocks. Like, if we want, we can reduce the voting period from 1,024 to say 256 or something less. But if we want an automated procedure, then some way or another, the ETH2 chain has to kind of come to consensus on some ETH1 block the real lower bound is basically what number of confirmations on the ETH1 side we consider to be safe, and then plus like how long it takes for the ETH2 side to come to consensus, right? Like the voting doesn't have to be as part of blocks. We can have votes come faster if we add some attestation mechanism, but then that just kind of adds a bit more complexity. So if we want, we can push it, say, under an hour, but and if the shorter we push, the more brittle the thing gets.
And just to make sure I understand, so you have like the last block, and then
Just to kind of summarize, you have like your last block, then you have say 256 or 1,000 blocks where you've kind of banned transactions on ETH1 through a hard fork or soft fork, and then maybe you want to keep mining those empty blocks, but maybe the EF just like pays outside of the chain.
Exactly.
Okay, cool. Thanks.
Okay. Question.
Could you summarize how an ETH1 client like a Guess would need to adapt to work in this new environment?
Okay, so an ETH2 client would basically everyone running an ETH2 client would have to run an ETH1 full client at the same time. So that's an increase from the current requirements, which are that every ETH2 node only has to run an ETH1 light client. So basically, if every ETH2 client is also running an ETH1 client, then the ETH2 that itself allows the ETH2 clients to kind of become aware of what the ETH1 full state is, and then after the cutoff, like basically, ETH1 clients will have to modify themselves so that instead of focusing on the proof of work chain, like basically after whatever the cutoff block is, they will kind of feed in blocks from the proof of stake chain.
Okay,
So
they just can forget about their proof of work mechanism.
Exactly, they can forget about the proof of work mechanism, and once the ETH2 side thing gets finalized, then the code that does any proof of work stuff can just be deleted. Okay, so I'll move on, and I will talk about kind of what benefits we get if we, instead of doing kind of ETH2 as this kind of rapid emergency transfer with ETH2 as phase 0.5 to the merge as kind of phase 1.5, right? So the big difference there is basically on the ETH1 side, we have this this roadmap, right, where basically one of the big things is we want to add stateless clients, and then there's also kind of some tinier things that I care about, like there's, I don't know, 1559, there's abstraction, there's possibly kind of more precompiles, but like stateless clients are the big thing, right? So if ETH1 becomes stateless client friendly, then the big advantage that we get is basically that ETH1 block verification becomes a pure function, right? So basically, on the ETH2 side, this kind of piece of data would actually have the block and it would also have the witness. And so you would be able to verify the block and the witness on the ETH2 side with just a kind of pure function call into ETH1 as a library, right? So you would not need ETH1 state storage, you would not need any of those other things. So this makes the transition easier because, first of all, it means that an ETH2 client does not have to run an ETH1 full client. Up until the cutoff point, all it needs is an ETH1 light client, right? Because if you have an ETH1 light client, then that's sufficient to learn the state root. And if you have a stateless client, then you don't need the full state. All you need is the state root, right? So if there's some cutoff over here, then all you need is you would just need to get the root, and you would just kind of transplant the root into here, and then there isn't this kind of magic call out into ETH1 state, and instead you would basically just be running a kind of pure function on the roots. And the other nice thing that this gives us for efficiency is basically that the root, well, because you have the block processing as a pure function, we can make ETH1 be a kind of one shard instead of making it be mandatory for everyone. And because basically what that means is you can have kind of different subsets of validators be processing ETH1 blocks. And so the load of processing the kind of relatively heavy ETH1 system can be shared, and every validator only actually gets that load, say 1/64 of the time, or even, well, actually only 1/2048 of the time, because you're only assigned to one slot on one shard, instead of it being something that everyone always has to deal with. And so, like, staking on your phone continues to be viable, as opposed to the phase 0.5 roadmap, where that becomes just totally crazy. Now, another thing is that as part of the stateless client roadmap, there's also kind of reforms that we might want to do. Examples of reforms that we might want to do. One big one is the hexary to binary tree. Another one is the two-level state to going to a one-level state. So we kind of merge, basically make contract storage just be part of the top-level tree. Another thing might be like, I don't know, account versioning, and like basically there's a bunch of kind of changes that we might want to do to the state, and there's also the possibility of like basically having some kind of pre-processing procedure happen at this point. And I personally, like, am kind of increasingly of the opinion that the safer thing to do is to have all of these different things happen at some point before the cutoff. So basically come up with ways for them to happen just on the ETH1 side. Both because periods up is at least I feel better than not splitting them. Like basically just because and if the more you split, the less risk there is in each part of the transition, and you don't have to kind of face all the risks all at once. And then the other challenge is basically that if you do these transitions as part of the transfer, then every ETH2 client actually will have to have an ETH1 full node of some kind, and this seems kind of not so desirable. Yeah. Unless, of course, the thing that you do is you just make the transfer be something that happens on the ETH1 side, but that kind of after the cutoff, but that's also risky. So yeah, and like my own kind of weak preference is definitely for this stuff to just happen before the transfer. Mm-hmm. So, okay, any more questions at this point? Yes. Mm-hmm. No, so this stuff basically, these are kind of changes to the Ethereum state structure. So like making the Merkle tree binary instead of hexary, making the state tree 1 level instead of 2 level, adding account versioning. How does the stateless client fit in? So for example, making the Merkle tree be binary instead of hexary is just necessary for stateless clients to work because of witness size reduction.
My question is,
did
you want one to be stateless client before?
Yes. So I'm basically, like, I'm arguing here that if ETH1 is stateless before the merge, then which in my opinion has the risk of basically kind of centralizing Eth2Real because realistically ETH1 is considerably kind of bulkier and more difficult to run than ETH2 is and is going to be. Yes. Okay, last question.
For the existing smart contracts that do not for stateless client, will they be able to automatically migrate to some kind of stateless form?
Okay, so stateless client migration. I imagine future presentations might also touch on this, but generally most contracts do not have to modify themselves at all to be stateless client friendly. So the one thing that stateless clients are going to mandate is that the gas cost of S-load is going to go up, the gas cost of external calls is going to go up, the gas cost of accessing code is going to go up, and possibly like quite a bit. But on average, we expect that gas costs of kind of regular operations are not going to change all that much, but there might be like weird outlier exceptions, and we do need kind of more tools to help, and we should be starting to develop these tools now to help detect these outlier exceptions. But that's more of an ETH1X thing than an ETH2 transfer thing.
And is there a plan for this database?
Which database?
The database that provides the state that is not on chain.
Okay, good question. So,
by the way, I like the word database.
Yes. Okay. So the only nodes that kind of strictly speaking need to store the database for that in the current stateless client proposals are the block producers. Now, if we do is if
so, how about this forking, right? So once you're syncing, you have this time where you take a blocks per range. So you aggressively ask for blocks, any chain from your pair, and just hope to end up over the finalized state. You verify the blocks, of course, but then, like once you reach this justified point, there starts to become this period where you may not have one canonical chain, but people are in doubt where to go. So you have a little bit of forking. And then once you're at the very end, you start gossiping about the very latest blocks, and you can have more forking. Like ideally, there are node forks, there's fast aggregation of attestations to determine the canonical chain, but sometimes you end up with bad luck, or there's some attack, and you need to transition not just fast forward, but you need to transition fast with all this backtracking to recover an older state and fork it to a new state. So let's analyze the beacon state. So what are all these fields that are being tracked and what makes syncing so tough? So there's these few tiny fields, don't worry about these. Like we have the fork version, slot data, a little bit about Ethereum 1 voting, but those are like very minimal constant size data. Instead, what you want to look at are like starting off with medium things, like these things only change one at a time. They make up like 10% of the storage size, depending on how many validators you have on the state. And then the larger part are also some more. These are necessary. And then like Ethereum 1, Ethereum 2 uses binary tree. I'll explain differences between tree types later. What you have to remember here is that previously, with minimal configuration, we only had like, say, 1,000 validators at maximum. Right now, we have test networks that are trying to push over 100,000 validators. So to do this correctly is really important. So let's talk about data structures. So there's this idea of persistent data structures, or say functional data structures, or immutable data structures, you may know. So what happens is that there's this collection that's backed by a tree, and then whenever you make a modification, you make a new tree represented by a new root referencing most of the older data. So you don't copy as much around. And this works really well with Merkleization, whereas with your binary Merkle tree, you have to redo a lot of work if you don't cache anything. Whereas with a tree, everything can be cached in place. You can put the hashes right at these binary nodes, and you end up doing minimal work. So in here, you only pay for this new branch from D star to E to do a more efficient update. So compare this to Ethereum 1, which has this Merkle procedure tree. I really like this old visualization because it explains it really well. But what it doesn't show is that it's really inefficient. So for your binary tree or for your Merkle tree, you want your witness data to be minimal. So that means that if you go back from a leaf node to the root node, you want the least amount of data possible to prove that it's there, to do like these fast minimal transactions on chain. Whereas this thing is more optimized for storage. So it tries to defragment the tree by putting nodes together. This blows up witness size, but it is kind of nice for storage. So we try and explore these trade-offs between storage optimization, having this fragmented memory, the amount of changes, the difference in finalized state, and so on. So let's talk about pruning. So Ethereum 1 has this nice property of pure finalization. So at some point, you can just trust the state, come back to it, and forget about everything that happened before the state on the beacon chain. However, if you do forget about this, you are not an archive node. You can only like serve others with like blocks from your storage, but you can't serve them with these older states because you don't have straightforward, fast access to them. So instead, what we can do, if we do want to take the optimized route, is use a finalized state and only put the diffs on top, the differences, to minimize the amount of binary trees used and have this faster iteration. Okay, so that's all the optimization and tree stuff. Let's talk about the validator client for a moment. So besides just running the beacon chain and syncing this thing, it should be like a little bit more clear now to you. We also have this separate client, which produces data on the network and participates in the network. So not just syncing, it responds to duties or like these tasks it gets from the beacon node. So the challenge here is like, how does it get these duties? How does it know what to do? So that's a lot about API design, and hopefully later when there are these different clients, about compatibility. So you can use different beacon nodes with the same validator. And then even when there is a bug or some problem with one beacon node, you're able to stay online with your validator. And then there's security, of course. You want to separate the validator away from the beacon node, away from the network, and protect it from all these attacks. So let's dive into APIs. So there's this APIs repository you can take a look at. Currently it only offers this really minimal API, so how to work with your validator. In the future we try and expand this, and we really need input from even from web developers to know like what kind of data do you need, how do you like it served, what's the best process here. For now it's just this really simple API. Then last but not least, testing. So one more challenge is to just get it right, and you never know like how many bugs are lurking there or like where to go from here. So what we do is we have these shared unit tests. So clients are not just writing their own tests, they also share these consensus tests. Then we have fuzzing, shout out to Mehdi and others from the Sigma Prime. They're doing great work trying to learn more about the beacon node, find these little bugs, and test the different clients. Then we have testnets. So all the testnet data that's public is on this repository. We try to actively share that, have community members open up a testnet, try it for themselves. Then we have the start of network tooling. So previously we had Whiteblock and others produce these gossip subtests or these more specialized tests. But right now we're looking into testing the full suite of networking. And you can try this REPL out, so to like start your own mocked node, be part of the libp2p network, interact with existing real clients, and see how they interact with the supposed specified networking protocol. And then there's audits. So I think it's to be announced, but we will have at least 30 audit results very, very soon. And with interesting results about networking, about possible DOS vectors. But we are actively working to make this like as resistant against these attacks as possible. And there's much more, like there's fork choice testing and integration testing of different kinds. I'm not going too much into detail, but if you're interested, do reach out. And we're also always looking for more like initiatives for people who would like to test the different parts of Firm too. This is the finish, and walkthrough completed. Congratulations, you're now expert on Phase 0. For real, if you're interested, there's this specs repository. There are many different documents that explain it in human words instead of a bunch of unreadable code. And you're actively trying to like onboard more people, find more contributors, and you're very welcome to take a look at the Ethereum 2 specification. Thank you.
Thank you, Proto. And the next one we have Ansgar, from core team to introduce the statelessness in Eth2.
Hi everyone. I just wanted to give a brief overview. That's pretty last minute. So actually, some of what I had here, that's the talk I gave at ETH222 a week ago in Stanford. Part of that will already presented, but I'll just skip over those parts. So basically, here. So we had this post a few weeks ago about state provider models in ETH2, and Will already talked about how basically we have these three different models. Here are the diagrams that you couldn't see earlier, so here they are. So basically, that's the direct push model. That's what we would go with in SSA. So there you basically only need state providers to get some initial state to the users. The users still need to get state somewhere in a stateless world. They could basically, if they really want to, they can just listen to the chain, just keep the state they need for themselves. But if they don't have sufficient state, they need to get it somewhere. Then they just create their transactions. They already include all the state they need. And then the transactions, just as in ETH1, just go to the mempool. And at some point, the miner/block proposer just takes them, bundles them up, produces a new block. That's it. That's the simplest model, but it requires SSA. Then we had this relay push model. I mean, it's a bit more complicated. Basically, the idea is you submit the transactions to like a relayer/state provider. They attach the state, and then they send them off to the network. And then we had this third model. I'm going over those a little bit quicker because they're not as relevant to this talk, right? But the pool model will mention that as well, where you basically have the block proposer will be responsible for fetching the state. You already know this, so basically the different advantages and disadvantages for direct push. We need SSA, but then we get a lot of things that we want to have. So yeah, that's why we started looking into it. Can we actually like get away with moving to SSA? Is it feasible? What are the benefits? First, I wanted to like give a quick definition again. It is rather imprecise, given that the whole wording around static state access. It's a bit unfortunate how that all came about. So we are still looking into other wording and stuff. But that's just like one rough go at it. So like basically, if you to define it on a transaction level, like any given transaction is like purely SSA if you can basically, and you see already how imprecise that becomes, if you can create a reasonably small witness for it, that basically is always sufficient to run the transaction. So what that means is you might not be able to completely predict what state it accesses, but maybe you can at least predict like it'll have to access one of these 10 different locations in state. And that's fine, because like a witness with 10 state locations attached is still really small. You can send it, everything is fine. But if those 10 locations maybe become 1 million, then you can't like send a 1 gigabyte witness, right? So basically, static state access really just means reasonably small witnesses that are always sufficient. So that's where that comes from. And then obviously, if all functions, all possible transactions you could create against a given contract are SSA, then the whole contract is SSA. And so our goal for ETH2 would be to have all contracts be fully SSA, if that's possible. Yeah, naming, we had a few different ideas here. We'll see how that evolves. Hopefully not as bad as the plasma thing got. Okay, so then benefits, those are just like a few that came to mind. So first you have like the simplified state provider model, you have synchronous cross-E communication, and it's also helpful for account abstraction, a bunch of other benefits as well. It's just, if we can have it, it's really nice to go that route. So the question is, can we actually get away with it? So basically what I've been doing for the 2 weeks before Stanford basically was to look a bit into like, does it limit functionality? Are there any existing projects that would have problems in an SSA world? And then what Sam has been doing was to like look into developer experience, this taint analysis solidity thing. How could developers develop contracts in an SSA world? And so, as Will already mentioned, I was looking at a few of the most popular DEXs first, just because DEXs are like one of the examples where we were thinking, well, maybe there are problems there because you don't really know the counterparties in all examples, right? So those are like really advanced examples of count day DeFi Ethereum usage. So the biggest one was Uniswap. So we started looking at Uniswap as the largest on-chain exchange. It is an easy example though, because Uniswap is not like a full DEX in the sense that it's one-sided, right? Your counterparty is always the Uniswap smart contract, so you don't actually have this full two-sided DEX experience here. And we, in order to like analyze it, we actually didn't look at the original Uniswap code, because that's written in Viper. For version 2, they'll transition to a Solidity version, but there is like an equivalent Solidity version as well, so we just went with that for the analysis. It basically just consists of 2 contracts. That's why it was easy to look at, right? You have this factory contract where every time you want to like create a new Uniswap exchange for a new token that is not yet, where there isn't yet any deployed exchange, you just call the factory and then you create a new exchange for that ERC20 token, basically, and then that deploys a new exchange contract. So looking at the, so basically the idea was that we quickly walk through the code there, so you can actually get a feeling for like what actually does it mean to be SSA instead of DSA, right? So that's like one part of the factory code. That's like the main function. That's where the factory magic happens in Uniswap. So you create a new exchange here. Basically, you can see in the beginning, if you just like very naively go through it and think about like where here could we have problems in a where might we not be able to predict state access, right? And in the beginning, you only have requires. You would always just those are no problem. And then if we go a little bit further down, we come to this line, right? It just deploys a new exchange, and here we see like one of the many examples of how, as we were talking about earlier, like for existing Ethereum 1, like DSA SSA just wasn't a like consideration, right? So it's trivial to like have like a contract deployment be SSA, but like the normal version, the create opcode, obviously like depends on the nonce, right? So if you have a contract, you deploy other contracts, then the address you deploy at depends on the nonce of the contract. So you can't predict at the time you create a transaction where the new exchange will be deployed at, right? But for example, even in Solidity, you can trivially change that because we have been having this nice create2 for a while. So if you just basically include like a fixed salt, then that's used instead of a nonce. In that case, it's just like as an example, you just take the address of the token as the salt, and then that's all of a sudden SSA. So that was all that was needed to make that line SSA. So that's just one example of how most of the changes that are actually needed to get to SSA for contracts are really just like technical, like trivial things, right? Nothing conceptual that's going on here. The only other part here where we also would have to have a look is down here, where we actually use an array to store all the exchanges that were deployed. And the unfortunate thing here again is that arrays, as they are working right now in Solidity on ETH1, would be DSA. And the problem here is again, like if you push to an array, right, you don't know actually, like maybe 3 transactions run before you, and they also like push to the array, and then you don't know the index at which you'll push to the array. But I mean, there are a few different workarounds. I mean, you can solve arrays for SSA too. That would be an issue. But you actually would have to adjust it somehow. But with those 2 changes, basically, the whole factory contract for Uniswap would already be fully SSA. And then to just very briefly look at to the actual exchange contract as well, just to have the thing complete. So first to note is that the Uniswap exchange actually is an ERC20, so it inherits from ERC20 because I'm not sure if you know Uniswap, they use like these internal liquidity tokens. If you provide liquidity, you get these tokens. Good news, ERC20 in its current form is already fully SSA, so no issue here. Then we just go through the contract a little bit. One more thing, that's just another general pattern. We are like, here we have like a very simple example of branching, right? We have an if statement. Exactly, and so basically, because it's branching, right? In this case, it's very trivial. You only have 2 cases. Either you get a refund or you don't, right? And you can basically just create witnesses for both cases. But again, you'd have to think about what if you have very complicated branching behavior, where there could be like a lot of different cases. So maybe you'd have to like find some way to deal with that. And then one more thing that you also can see, the same thing here is the transfer function. And again, basically all that's relevant here is that if you actually send ETH to the buyer in Ethereum right now, you'd basically, if the buyer is actually like a contract, you'd execute its fallback function. I think it has a new name, right, with the new Solidity version. But basically the fallback function, the function that's called when you get ETH. And in case that function is not SSA itself, there would be a problem here as well. Yeah, but basically with those little caveats, basically Uniswap would already be SSA. So you'd fix these, you just find solutions for them, and then Uniswap just works in ETH2 even if we go with SSA. So that was encouraging. We also looked at a few, oh wait, wrong direction. We also looked at a few other DEXs, but I didn't want to go into too much detail, but just it's fair to say like the second largest IDEX, it's a full DEX, but as the matching of the orders is actually performed off-chain, right? So you find the counterparties that want to trade with each other, and then you just basically match them, and only then do you execute the trade on-chain. All of that also would work in SSA, so that's the contract here, but it just would work. So that's basically our first impressions. SSA for ETH2 seems feasible, and because we have all these benefits, right now we basically want to explore, like go down the route of using SSA. Obviously, if at some point we find any problems with it, we might still like change our minds. But for now, it looks like SSA is the way to go for ETH2. Further analysis is, however, necessary. Also, like one important thing that I wanted to not forget about is like, are there maybe further future use cases that aren't used right now by projects on the chain that would be problematic in SSA? Those obviously we also want to be like future-proof, so we look into those as well. If you have like any questions or comments or whatever, you can always reach out to me to discuss that further. But that's basically all regarding the feasibility. And then I'm not sure, Sam, if you want to quickly talk about the taint analysis. I'm not sure I'm not sure who here in the room has like an overview about the time that's left.
About 10-15 minutes.
Oh yeah. If you want to like maybe like just a few words. Do you have the Oh yeah, sure. If you have any questions regarding this SSA thing right now, obviously, sure. I'm not sure if there's like a mic we can. Yeah.
Are these solely the SSA shorts for the ETH2 world, or does this equally apply to ETH1X transition to a stateless model?
So this is just like if we transition ETH1 to a stateless model, it could still remain keep its dynamic state access patterns. So just because like moving all contracts to a SSA pattern seems to be infeasible, right? I mean, most contracts would have to be redeployed, and so the plan right now is most likely to just keep Ethereum 1 as DSA for the foreseeable future, and still move it into ETH2, but have like special handling of that, so we can support DSA there, but have the rest of the ETH2 system be SSA. So, but our top priority obviously is not to break any existing contract, so we won't.
Just to add to that, if it wasn't clear, so between DSA and SSA, it's only really different for the proposer and for people that create transactions. But on-chain, it's the same. On-chain, it's still the same witness data. You get to verify the block. And so making this a kind of special case would not necessarily mean this huge amount of legacy software. Like on-chain, we can introduce it very well.
And also, just maybe that's too confusing, but even in ETH2, even if we go with SSA, you could technically still like have DSA transaction make it into blocks, because they would be just as valid. It's just that usually, basically, they wouldn't be able to make their way to the block proposer, because by then the witness wouldn't be sufficient anymore. But if you, for some reason, basically, if some block proposers wanted to choose to also support DSA in some complicated form, they could always do it. So basically, SSA is just limiting ourselves to make the system more easy. We can always then go like add functionality back for ETH2.
Hello.
Hi.
I'm quite skeptical that SSA is feasible if we want to retain the current functionality of the ETH1 chain. I mean, there's plenty of examples, and I could list a few that I think would be difficult to do. But as a sort of general remark, we can think of anything that is front-runnable being something that would be DSA, right? Because the semantics would change when another transaction is squeezed in. And there's quite a few things that are front-runnable. But maybe the more general remark is, say that we don't, given that there might be, even if they are constructed examples that wouldn't be possible with SSA, what would be our sort of rationale for calling those examples pathological and saying that we don't really care about their functionality? Because there will always be somebody's app that will break if we go with pure SSA.
So I think that's like a two-part question. So first off, I agree that there might definitely be examples that are problematic, but I assume at least you might think it's more problematic than it really is, because the issue is not with like the state changing before you run your transaction, because that's not an issue. If I basically create my transaction and I believe the state will be in a specific state, but then before my transaction actually gets run, the state changes, that's not an issue. Then you can, like nodes in the network can always just like update my transaction while it is pending. So if I basically want to do is want to send a transaction to Uniswap, but someone else does a transaction first, then obviously the rate at which my exchange will happen will change. But that is fine, because my transaction doesn't actually it has data with it that it wants to use to run the transaction, but the data can be updated if someone else changes it beforehand. It's only problematic, this very specific use case, if the location at which I want to use the data changes. And that's like a small subset of
well, I think that's a larger subset than you seem to apply. For example, the deposit contract has this feature that when you place something in a deposit, it's dependent on the deposit count, and so if somebody goes before you, then it ends up at a different location. Also, all the auction contracts where the winner of the auction is something determined by the current highest bidder and stuff like this, which is powering the Maker, for example, or stablecoins like this.
I believe for most of those you can actually work around that and make that SSA. I'm happy we can definitely talk. And actually, the whole point here was to explain what is SSA good enough that enough people understand what the question is, so that we can then see if anyone can come up with real problems like use cases, legitimate use cases, and that's the second question you had. What's the difference between a legitimate use case and like an edge case? To then see whether it's feasible. And then just very briefly remark on what is a legitimate use case. Obviously, we always have to choose trade-offs. I feel we can definitely go a little bit with not like supporting use cases that definitely look like they're just arbitrarily constructed, just because this is just how what kinds of use cases ETH2 will support, right? You can always remain on the ETH1 chain even within the ETH2 system and have full DSA support. So we don't want to break any existing use cases. It's just what will we enable for additional use cases for ETH2, and so we can be a little bit more aggressive in not supporting anything, right? Just for legacy reasons. So we would actually look at, is that a legitimate use case? And as soon as there are problems with those, we would reconsider. But if you just come up with a artificial constructed one, and we actually came up with artificial things that wouldn't run anymore, right? If you go with block hash things, and so you can construct use cases that might not work anymore, but those are really weird edge cases. And we can definitely let's talk afterwards and see whether any legitimate things would also be problematic.
Sweet, thank you.
Awesome. I think that's it from my side. I'm not sure if now Sam or not. Well, I'll just be gone. But thanks, guys.
Thank you everyone for attending this, and sorry we don't have enough time and have a good time scheduling here. Yeah, thank you. sure. Not sure. So, yes. Sorry.